OK, good morning, everyone. My name is Gil Forsyth. My colleague Philip Cloud is here in the front row. You'll meet him later. This is going to be the Ibis tutorial. This is a hands-on tutorial, so you should connect to the Wi-Fi and clone the repository if you haven't, and install the environment. I know this is a lecture hall, but we're going to pretend it's not and do more of a classroom style. Philip has got a pack of Post-it notes. If anybody here is familiar with the carpentries, we're going to do something a little bit along that style. So as we're doing exercises, we're going to give each of you a Post-it note. And just while you're working on the exercise, just slap the Post-it note on the top of your laptop. And when you're done, take the Post-it note off. It's a way for us to visually gauge who's still working on things without continuously asking, is everyone finished? And then making you feel pressured for no reason. Also, I have a tendency to talk very quickly. Feel free at any point to tell me to slow down. And if you have any questions, please interrupt whenever, although I guess interrupt by asking for the microphone so that that's recorded as well. OK, thank you. Please interrupt by raising your hand. Please ask questions. Philip will provide the microphone for everyone who needs the microphone. Do you have the? Where did that go? Oh, OK, great. Has everyone, a show of hands, do people have this repository downloaded yet? OK. OK, so if you don't, please connect to the Wi-Fi and clone this repository and create the environment that's listed there. If you don't have a laptop out, this will be less fun for you. OK. I'm going to start with just a few slides, and then I promise no more. This is just to give a brief overview of what Ibis is. Maybe you know already because you're in this room, but maybe you don't, in which case, just to walk you through it. So this is the Ibis tutorial. If you don't want to learn about Ibis, you are in the wrong room. I am Gil Forsyth. This is Philip Cloud. We work at Voltron Data. Here are some places we are on the internet. Generally speaking, the PyData stack, this slide shows up in every talk at a conference, right? Makes two assumptions. One is that data is or are local, and the second is that data fits in memory. What in practice that ends up looking like is that if you have, and these are just representative, say pandas and Postgres, you connect to your remote engine. You ask, do you have a table called ratings? You slurp up the entire table over the wire, and then you do all of your analysis locally, right? You load the data, you parse the types, you perform some analysis. This is fine, but it's doing a few things that could be better in a couple of ways. For one thing, if your laptop doesn't have enough RAM, this just doesn't work, right? If you're out of memory, you're done. Secondly, the thing on the right is usually pretty powerful. And you might be leaving a lot of performance on the table because Postgres is a lot faster at doing some things like aggregations and sorting. And this leads to what we sort of call the PyData translation problem, which is that there's usually a mismatch between the tooling that's available on your laptop and the tooling that might be available in either a distributed setting or a production setting in the enterprise. And so you end up in this horrible place of having to maybe prototype something in pandas and then rewrite it in PySpark. So Ibis tries to get away from that. It does this by following a deferred execution model. So if you consider this same scenario where we have our laptop on the left and a remote engine on the right, now instead we connect to the engine. We say, do you have a table called ratings? And if the answer is yes, we just get back the schema of that table. That's it, just the column names and the column data types. We use that to build up a deferred expression where we validate and then compile the SQL. Then we send the SQL over the wire to the engine, have the engine execute it, and then we only pull back the results. So especially if your query ends in, say, like a count of things or the top 10 values, or you just want the results of your aggregation, you are pulling much less data over the wire. And also, the engine is almost certainly faster than your laptop. In this scenario, if your laptop is a Raspberry Pi, that's fine, right? Because what matters is that the thing on the right is big and fast. And usually the thing on the right is also much closer to the data, especially if you're dealing with cloud warehouses. Some fun little things that come out of this also is that the thing that gives you the metadata for the table doesn't necessarily need to be the engine. It could be some metadata store instead. Or you could just define the table yourself without ever connecting until you're ready to execute. You just say, here are my column names, here are the data types, and then compile your query and execute it. OK, that's all the slides. No more. Most of this tutorial, is this big enough for people to read? Yeah, great. So? Yeah. Bigger? Yeah, definitely. Maybe. Hold on. Yes. Is that up to date? No. If you have not done, this doesn't seem right either, does it? Please install these things. This is a play as you go tutorial. So ideally, you can be running these commands as I'm running them. There are exercises also for you to do as we go along. Quick show of hands, who does not have the notebooks on their laptop right now? That's OK if you don't. I'm just checking. OK. All right. I'm going to give you 2 minutes. Also, if you need any assistance getting notebooks on your laptop, please raise your hand, and we can roam around. And I'll mute myself, too, so I'm not announcing it to the room. Also, while we're getting everybody set up, if you do have these notebooks, please go ahead and run this first cell here. That'll download a small sample database to your laptop, and we'll see what happens with the conference Wi-Fi. Okay, everybody, let's get going. Once again, just a quick reminder in case you came in a little bit late. The Post-it notes that are being handed around while we're working on exercises, just put them on the top of your laptop so we can see that you're working. And then when you're finished, just put it on the, just put it down. Okay, I think we'll go ahead and get started now. All right, so Ibis works with many backends. When we say backend, we're usually referring to things that are SQL engines, but this also includes things like Dask and Polars and PySpark. But what we'll mostly be using today are SQL engines, largely DuckDB, which is one of our backends. It's the default backend. I'm just telling you this so you know what's actually running on your laptop. You don't necessarily have to care. The idea is that whatever system is available in your institution or organization or just on your laptop, Ibis can usually talk to it and use it to execute computations. We're using DuckDB because it, kind of in a similar fashion as SQLite, is a local file-based database on your laptop. Unlike SQLite, it is screaming fast and designed for analytics. SQLite's great, it's just a different system. So if you've run this first cell, then we should be able to connect to that database. And this is usually the first step of any Ibis process, which is you connect to a backend. In this case, we're connecting to this Palmer Penguins database we've downloaded. And then once you have a connection, you usually want to see what data are available. So to do that, we call list tables. And you can see, hopefully on your own machines as well, that there's only one table in this file, which is called penguins. And so we want to pull that table out and get an object that we can interact with. So we do that by calling con.tablePenguins, give the name of the table. And then you can see that the repr of penguins tells us that it's a database table. And Ibis cares deeply about data types, both because data types are important, but also because the backend cares about data types. Postgres cares. SQLite not so much, but most of the others do. And you can see we have several column names: species, island, bill length, etc. And you can see the associated data types of each of those columns. This, to start with, is the only thing Ibis pulls from the database. It just asks for a list of column names and data types. And at that point, there's no computation happening. This is just things we're inspecting. We can request computation by calling one of several methods. For instance, to pandas here. So I'm going to call head, like you would call in pandas, for instance. But then I'm going to say to pandas, because I actually want execution to happen. And you can see this is the, if you're not familiar, this is the penguins data set. It's just a fun little data set to play with. So we get back the first 5 rows of that data set as a pandas data frame. If you want to use pyarrow instead, you can say to pyarrow. We'll get the same data, not as beautifully rendered in a notebook, but it's all the same and still there. If you only call head, what you're going to see by default is this sort of deferred representation. Ibis is a deferred execution model. It only executes when you say, like, give me the data, please. So what this is saying is, like, well, you stacked 2 commands. One was, I have a table called database table penguins, and you asked for head, which in this case is just give me a limit of that table where n equals 5. So that's sort of what's underlying there. When you call to pandas or to pyarrow or to parquet or to CSV or to whatever, that's when this will actually execute and do something. For the purposes of a tutorial, and often when you're doing local exploratory data analysis, we'll turn on interactive mode. So everything I just said about deferred execution is still true. We're just going to slightly ignore it. And ibis.interactive, or options interactive equals true, is going to more eagerly execute things. So it can just display the first 10 rows of your result. So this is a good way to learn how to use Ibis. And if you're exploring a data set, you don't have to. But for the purposes of an interactive tutorial, it makes a lot more sense to me. So now if I call head, you'll see this formatted table, the same data. But so remember that each time we run a command, we are going to be executing these things just enough to show data. So for head, that's a very light execution. If we call a sort, there's a bit more that's going to happen. But DuckDB is fast, so we'll be OK. All right, so we're going to start by going through just some basic operations. Who here actually knows SQL? Show of hands. This is great because like everyone sort of did what I do, which is, yeah, OK. That's great. So like some of the terms will be familiar. There's only one part where I'm going to make you write any SQL, and it's like fill in one word. I promise. That's it. I feel the same way. I'm like, the one time I wrote that query and it sort of worked. OK, but some of the verbs are the same, so it's helpful. If anyone also is familiar with dplyr in R or dbplyr, this is a very similar model. All right, so if you want to perform a filter, which would say let's subset the data somehow, you can call filter and then give it some kind of comparator. So in this case, saying I want to see only the penguins where the species is Adelie. And that'll work. Now we only have the Adelie species there. And you can stack filters. You can provide multiple filters. So for instance, if we want to only see the penguins that reside on the island of Torgerson and are Adelie penguins, we can do that too. You'll have to trust me that there's no other islands down here. But for multiple filters, I'll just point out quickly, you can use the ampersand here, but each item is going to need to be encased in parentheses. That's just because of Python. Or alternatively, you can provide those individual filters as a list of conditions. So you can stack as many filters as you want. This is helpful in a composable model where you can filter one thing and then just keep adding filters as you go. You don't need to find the right part of your SQL statement to insert it into. Ibis will do that for you. So that's that same filter. I'll actually quickly just show this off. I realize I didn't mention. What Ibis is actually doing when you run this is it's compiling this to SQL and then executing that SQL. Right? So that's the command that's actually being run. So I'm going to show you lots of SQL, but we're not going to write any of it because this is better. But so you can see, very straightforward, select all the columns from the table penguins where the island is Torgerson and the species is Adelie. Philip, can you run the microphone to that gentleman there, please?
Thanks. I'm just curious, what if I wanted to filter by another database, for example? Then is it all one SQL query somehow? Or
let's come back to that.
Work?
There are experimental branches that will let you do that. Usually we try to stay within the same database because things get very hairy otherwise. We do have experimental branches with names like hellscape joins and do not use this, where you can do that by dumping everything into PyArrow and then stitching things together. So it's doable. But that'll be for the advanced tutorial that we'll hold next year, I think. But we're happy to chat about that later, too. All right, so that's a simple filter operation. If you want to select, that just means to subselect down the columns. So for instance, if we only want to look at the 3-column species, island, year, you pass the 3-column names in, you get the 3 columns. You can probably imagine what this SQL statement looks like. Yes, Mike.
I have a quick question about if can you go back to the filter thing? When you do the double equal, does it do execution already, or only when you do it filter? So I just want to know, can I prepare the list with the conditions beforehand without doing anything, or this is eager or lazy at this point?
This is all deferred. So this is like only in Ibis land is anything being executed, and it's really just we are creating those conditions in the expression we're going to execute. But nothing's hitting the data. The only reason that we're hitting the database right now is because we're in interactive mode. But otherwise,
okay, so I could write a list comprehension preparing this list with the conditions and store it, and later on give it a filter, and that would execute it, and then something would happen.
Yes.
Yeah. This. Okay. Mm-hmm. So if you do a list comprehension and you have a complex one, then you can kind of pre-store the conditions and then later on just say, "Those are my conditions," and apply them.
Yeah, so long as the object that's in that list comprehension is an Ibis table, whether it's an unbound table or a database table, that will work just fine.
Okay.
So you can see this is what's actually being generated by that command if we're not in interactive mode.
Yeah.
So all that's being said is that we know that there is a column called island and we know there's a column called species, and we're just going to stack those into the expression. So you can feed it with a list comprehension or a generator or whatever else.
Just prepares the SQL statement, but nothing happens yet, and then when you send it, then it's doing.
Yeah, in fact, it doesn't even prepare the SQL statement until you say go. At this point, it's just building it up in Ibis.
Recipe for the SQL statement.
Yes.
Mm-hmm.
Yep.
Okay. Thanks.
Yeah. I should also point out too, just we would come to this later, but if you, for instance, try to say like island less than or equal to the number 1. Ibis will error before you ever hit the back end because we're doing data validation, but only with the data we know. So you can only perform operations that make sense on the data types you have. If you try to capitalize on the number 4, we're going to error. So it sort of stops you from hitting your back end until we can promise that the SQL we generate will execute. Not that it'll be correct because you might, not that it's what you want, but it will execute. Okay. Thank you, that's a great question. Put interactive mode back on. All right, so back to selection. We can subselect a number of columns. What am I pointing out here? You can either, oh God, sorry, I don't use my laptop mouse a lot. You can select column names either by the name, by just passing in the string names of those columns, which is what I've done here on that first one, or you can use attribute access, so you can prepend the table name there. This can be helpful because these will tab complete if you're using them. If I have this, I can do that. Or we can not download Firefox. You can also mix and match them. So you can see here I've provided sort of 2 column names just as the string names, and this third one is the attribute access. This will all give you the same thing. All right, that's just selection. Mutation allows us to either add columns that are made up of other columns. So in this case, we might create a new column where we have currently the bill length in millimeters. If we wanted to have it in centimeters, we'll say, all right, we want a new column called bill length cm, which is equal to the contents of bill length mm divided by 10. If you run that, you'll see that we have all of the same columns, but if you scroll over, there's now an additional column here, which is the same values, just in centimeters instead of millimeters. Okay? All right. I'm so sorry about this. This is our first exercise. I actually genuinely feel bad about this. I'm regretting my decisions. But your PI is a cranky American biologist who thinks the metric system is for suckers. He's a fool, and we're sorry. He demands we convert all existing measurements to inches and pounds, respectively. I am so sorry. The PI is extra cranky this morning, so we had better make sure that only those silly units are visible in the output. So some helpful / cursed conversion factors you can use here. For millimeters to inches and grams to pounds, let's ignore the fact that we're going from a weight of mass to a weight of... This is terrible. We can all agree. 2 things you might use to accomplish this that we've just covered. You can use mutate calls to create new columns. And then you can use .drop if you want to remove a column, or you can use select to create new columns and select the columns that you want. So I'm going to give you all a few minutes to try that. And then we will show you some answers and talk about other ways we can accomplish things. So if you want to go ahead and put the sticky note on the top of your laptop while you're working, and then if you have an answer, you can then take the sticky note down, and that'll help us sort of figure out how things are going. And feel free to raise hands, and we can roam around while you're working, too. OK, I see a few people are finished. So I'm going to go ahead and start walking through this a little bit. Feel free to not look at the screen if you're really close and you just want to get there. I also promise this is the last example where we use imperial units. I won't do this again. So we said there are multiple ways to accomplish this, just as there are multiple ways to accomplish this in SQL or pandas or Dask or whatever you want to use. One is to first do a mutate call and then a drop call. So what that looks like is first adding in the 4 new column names by saying inches, 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 pounds, and the respective conversion factors. And then dropping the original column names that have the same units, so that, man, that touchpad is very jittery. And so you can see if we do that, we've added these 4 new column names, and then we've removed the 4 original columns. So just again, we do a mutate call for the 4 conversions, and then drop, which I think I actually forgot to mention earlier, I should fix that, to remove the existing column names, because we don't want to have the duplicates there. And notice you can always just chain commands on arbitrarily through just calling more and more methods. Philip, can you run the mic over to Olivier?
So I tried to do the same, but by passing penguins.attribute names in the drop section, but it's invalid, and I'm not sure why.
Oh, that seems like a bug.
Okay.
That should definitely work. Yes, Guillaume? Oh, sorry, can you run that?
Is there a way that instead to have the new column names basically as variables, if you have a string, do you have a way, for instance, to make a disk comprehension, then you replace some things with like the millimeters by inch, and then you want to pass kind of like a dictionary of things or whatsoever? Is there an API?
Yes. Wait till the second notebook, and we'll cover exactly that.
OK, thanks.
Okay. All right, so that's one. The other way to do this, or another way to do this, is you can do this in a single call to select, because select will also let you pass in these sort of mutate-like calls. So you can say you want these first 4 columns of species, island, sex, and year, and then another 4 columns, and this is sort of the same contents of the mutate call above that create those on the basis of the existing data. And you can see that those will give you the same results. Luckily, because we're not actually mutating the underlying data, right? This is all a construction on top of what's there. So now that we're done with this exercise, we don't need to think about pounds and inches anymore, and we haven't corrupted our database underneath it. So again, apologies for that. All right, so moving on. So we've done select, filter, mutate, and implicitly drop. So now we're going to look at a few more sort of basic operations before we move on to things that are slightly more involved. So the first is order by. This is often also called sort. We use the SQL lingo here. And so for instance, if you want to sort by a column, you pass in the column name either as the string or as the attribute access. And then I'm just selecting a few of the columns just to make it not quite as wide in the output here. So we're sorting by flipper length. By default, and this is usually the default in most SQL backends as well, we sort in ascending order. If you want to sort in descending order, then if you're using the attribute access, you can call .desk on that, and that will give you descending. Or additionally, you can call ibis.desk on the string name of the column, and that will accomplish the same thing. So then you have that column sorted in descending order instead. Okay. All right, on to aggregates. So there are several aggregate functions available in Ibis, things that you're used to, like mean, max, min, count, sum, and more. You can aggregate a column just by calling the method on that column. So the mean flipper length in millimeters is 200 and change. Or you can add multiple aggregates. I'll also say ag is available just because typing aggregate may be a little bit, it's long. But they do the same thing. And so you can call an ag and then say, I'd like to aggregate over the mean of the flipper length and the max of the bill depth. And that will give you those two values, right? So this is the mean flipper length of the entire data set and the maximum bill depth present in that data set. So if you just want some vital statistics really quickly out of the entire data set, that's sort of your aggregation over all the data. But realistically, most of the time, you're going to want to probably combine this with a group by. Right? So group bys create groupings of rows that have the same value for one or more columns. If you just call group by, you'll see you don't actually get anything out of it. You need to call aggregate or ag on it to get something useful. So if you actually just call ag without anything, you'll see that actually will sort of just give you the unique values of a column. Right, so if I group by species and call ag, there's nothing there. It's just going to show me what the unique values are. There are 3 species of penguins in this data set. Similarly, if you wanted to group by multiple columns, you can pass them as a list. So here, species and island. If we call ag, we're going to get the distinct values that are distinct across both those columns. Right, so then this is sort of that set of all the combinations of species and islands of penguins. But instead of just calling an empty ag, if we actually pass a more meaningful aggregate, you can start exploring the data in a lot more useful way, I think. So in this case, we're going to group by species and island, and then aggregate over that by the mean of the bill length. And so now what we've done is we have, for each species of penguin on a particular island, this is the mean bill length for that species. Right, so you can begin to see if you need to slice and dice your data, it's pretty easy to pop all this together. And just for giggles, if we want to see what that SQL looks like, it's actually not too bad. Pretty good. And just as before, we were adding multiple aggregates. You can do the same thing by adding multiple aggregates to a group by. And so now you can see for each species on each island, here's the mean bill length and the max flipper length. And you can see how all of this can compose together. You can keep adding more things to the group by, more things to the aggregate to get whatever data you are after, whatever answers you're trying to find. And the more groups you add to the group by, the more distinct groupings you create, and the more groups you calculate all of these values for. Right? So it's easy to expand the dimensions and like the cardinality of your final data set to compute all of these sort of vital statistics. Okay, so that's sort of our rough intro to select, filter, mutate, group by, order by, drop, aggregate. So let's try to answer a few questions about penguins, because we like penguins, hopefully. So there's a few quick exercises in here. First is just to determine the largest female penguin by body mass on each island in the year 2008. And the second is to find the largest male penguin by body mass on each island for each year of data collection. So I'll give us about 3 minutes for that, and then we'll move on. Okay. So for this first exercise, and I'll just point out there are multiple ways to write these queries, so if yours doesn't match this, that's fine. One is to first filter down, so we only have female penguins, and in the year 2008, so that's subsetting the data there. Grouping by island, and then asking for the maximum body mass. You can also, for instance, have called an ag here if you're going to do that. But no, you can't. I lied. Don't live code. Similarly, for the second exercise, there we're just filtering by island and year, and then calling body mass to get across each of the islands. And sorry, in each year, rather. Okay. Really quick, I'm just going to go through these things. We're not going to be using these in the rest of the tutorial, but just so you know, they're there. Often when you're loading data, especially from CSVs, things will not get typed correctly because CSVs don't have typing data. So if you need to cast something to a different data type, that's always available. So if you wanted to, for instance, cast the bill length to an integer 32, that's no problem. If you wanted to cast a year to a float, I don't recommend that, but you can. And you can cast numerics to strings if, for instance, you wanted the year to not behave like a number for the purposes of performing arithmetic. If you try to, however, and you can cast numeric strings to numbers. If you try to cast a non-numeric string to a number, Ibis is going to yell at you and won't let you do that. And the final thing, just drop nah. If you need to get rid of nulls, just call drop nah. It's the same as pandas, just to remove all of the rows that have null values in them. And then finally, just before we move on to the next notebook, I would suggest you just del the con there, because we're going to use the data set again later. And this has a lock on that file, so just to clean it up, just do that. OK, hush now. Thank you. All right. Now if you want to go ahead and open up the next notebook, which is number 2, and we will continue onwards. All right. So the first thing here we're going to talk about is mem tables. So the first thing we did in the previous notebook was I had you download that Penguins database, and we were looking at that. Oftentimes you maybe already have data on your laptop in memory or in some other format that you want to use. So this is sort of a selection of different ways to kind of get that into an Ibis accessible form. So we're going to import Ibis and pandas and PyArrow and turn on interactive mode. And then here I just have 3 small toy data sets in sort of different formats. So the first is just a dictionary. So you see that we've got things that maybe look like columns of name, committed, aliases. Got some names and some numbers, and then some strings. There's a PyArrow table that I'm creating from a Python dictionary in this second one, and then just a pandas data frame. And so you can call ibis.memtable on any of those things, and they will work. So you can see that first plain dictionary gets rendered as a table. You can see that the PyArrow table is also loaded in, and the pandas data frame. I'm also printing out the schema here, so you can see that the data types of the input data where it has data associated will match, right? So if we have a string and a double in that PyArrow table, we will get string and double in the output there. Similarly, pandas, things that are object types will be typed as strings, booleans will be bools, so on and so forth. I don't know what Just happening there. OK. So joins. We've just been working with one table up to now, but most of the time you're actually probably working with data that are stored across many tables, and you join them together. So that's what we're going to do. So if we use some of those mem tables that I just created, we're going to try joining those together. So the simplest join is this inner join, and you can just pass in the column name you want to join on, and that will work just fine. This assumes here that the name of the join column is the same in both tables. If it's not, you can pass in, it's still the same, but here you could pass in more explicitly. You want to do like the first table, use the name column. The second table, use the name column as the join condition. You'll get the same thing. If your two tables have naming collisions in the columns, then Ibis is going to rename by default the columns on the right-hand side of the join. So you can see here that both tables T1 and T3 have a column called committed. And so the one on the right is going to get renamed to committed_right. This is just to stop you from losing your mind. And if you want to, you can specify different naming schemes for those collisions and how you want to handle them. So you can pass in this lname or rname format string. And you can see that in this case, that'll also add, for instance, like the left rename to the left-hand side committed column. Or if you wanted the kind of the rename to happen with a prefix instead of a suffix, you can do that too. So here instead we have right committed. The default join there is an inner join, but if you want to do outer joins, semi-joins, anti-joins, all the joins, you can. You can do this in two ways. One is to pass in this how keyword argument to join, which is like what kind of join do you want to do. So if you want an outer join, you'll get an outer join, which in these two tables doesn't make a lot of sense. But there are also, sorry, am I scrolling? There are also join-specific methods. So there's an outer join method as well. They do the same thing. This is just sort of what you want to, how you want to address it. And you can also chain joins. So if you want to join T1 to T2 and then join the output of that to T3, you can just keep passing join in, and that'll work just fine. Which brings us to the deferred operator. We did this join a second ago with T1 joining to T3, and we had, because there's this naming collision, you end up with committed and committed right. And whatever we wanted to name it, there's going to be a column that's getting renamed because of the naming collision. If you want to filter, let's say, after you've done this join on that renamed column, it sort of presents a bit of a quandary, because that column only exists in the aftermath of the join. It doesn't exist before it. And so it's sort of a tricky question for how to address it. So in this case, we would have done maybe, given the first notebook, is say t1.committedWrite, because t3.committedWrite would be the attempt here. This shouldn't work. Yeah. Because there is no committed write column in T3. There's only a committed write column in the join of T1 to T3. So one thing you could maybe do is a lambda function. Be like, well, I know I'm going to pass something in. And whatever that is, just choose some column named committed write and say that's true. And that does work. But writing this out can be a little bit awkward. So the other option you have is this underscore operator. So we import underscore from Ibis. I will note that, yes, this does collide with the usage of underscore in IPython and other things. Sorry. You can, if you really don't want to use this, you can always import deferred and rename it to whatever you want. We just chose underscore because it's convenient to type in short. And so what you can do now is that same filters above. We join T1 to T3 and filter on the renamed column in the output of the join by using this underscore to refer to basically whatever came immediately to the left of that command. Right? So it's always the most recent output of the thing you've done. And what this means is that you can use this to continuously refer to things that were that happened in the previously chained method as you are going through your analysis. So if we join T1 to T3, and we then relabel committed write to instead have the name has committed, then we can filter on has committed by just referring to the underscore, because the underscore in this case is equal to t1.join.relabel. And then in the next line, we can similarly use the underscore to refer to the joined relabeled filter. And then in the next line, we can use the underscore to refer to the joined relabeled filtered mutated table. So it is always just equal to whatever came before it. And so it's a way to be able to just refer to the things that have come. This has a couple other uses that come in kind of handy. For instance, if you have this table, you've just given it a long variable name, you can write that out. Let's say you wanted to find the aliases that begin with the letter S. It's just sort of an awkward-looking command because you chose a long table name. And you've got this long descriptive name, but now you're typing it a whole bunch. You can, the same way, just use the underscore operator to refer to the thing that came before it, which in this case is just this table name, which can make it just a more concise way to write the same things. Yes, we've got a question there.
Hi.
Hi.
Can you go back to the underscore operation?
Yeah. This one?
Even further? What will happen if you change committed right into committed, let's say, left? And this one doesn't exist, I think.
Okay.
Okay, so it does the check. Okay, thanks.
Yeah. Yeah, we and sorry, so this is an error from Ibis, not from DuckDB. Like if we had compiled that and passed it into DuckDB, DuckDB would have errored because there is no column with that name, but it doesn't get that far. Ibis will stop you by saying that, well, you know, it's going to compute the chain of operations, and it's going to get to that point and say, I don't have a column by this name, and then it's going to barf. Okay, so for this next bit, we're going to play with some joins, but instead of using fake data, we're going to grab some IMDb data. So go ahead and run that cell there, which should download things. I think these are pretty small. I subsampled them so that they weren't huge on conference Wi-Fi, and hopefully that doesn't choke everyone's laptop. Sorry, this should be IMDb small. Yeah, so you should have these two Parquet files. I'll give that 30 seconds really quick. Okay. So in the previous notebook, we were using that Penguins database that we just downloaded. That was a DuckDB file that I prepared before the tutorial. But if you don't have someone preparing you a DuckDB file, what you often have are CSVs or Parquet files, if you're dealing with data you've downloaded from somewhere. And those are easy to read into Ibis and DuckDB. So in this case, we're going to create a DuckDB connection, but instead of connecting to a file that already exists, like a database file, we're just going to create an in-memory connection. So we just pass in nothing, which means this is an ephemeral connection. This is still going to be able to operate on data way larger than the RAM in your machine. It just means that we're not going to save anything. And then we're going to call read Parquet on these two files. I'm also specifying the table names I want. So in this case, IMDb title basics and IMDb title ratings. And you can see that once we've read those in, that they show up as available tables. And then similar to before, you can pull those tables out. I think actually before what I did was this form of calling con.table and then passing in the stringified name. That is just fine. If you want, there is this convenience method called tables, which has tab completion. So if you don't want to type out the table names, you can do con.tables instead, and then just select the attribute there that corresponds to the table you want. You can see that basics is this IMDb data, which has sort of an ID key, the type of thing it is, whether it's a short or a film or a TV show, the title, the original title, whether it's an adult film, the year it was started, because some movies like Fitzcarraldo took 14 years, runtime, genres. And I think I forgot to show you ratings, which is those same identifiers, but then just the average rating and the number of votes that each of those titles has received on IMDb. So do a quick join exercise here. We want to join basics with ratings on the column tconst. And that should be pretty straightforward. Fingers crossed. All right, so that first one, we just call basics.join, ratings, use the column tconst. And now you've joined together the data, and now you can see that average rating and num votes are present in the same table. This is sort of a lot of data that we maybe don't care all about. So in the next exercise, we're going to do the same join. So basics to ratings on tconst, but then only select these four columns. So title type, primary title, num votes, and average rating. Bless you. Okay. In the interest of time, I'm going to keep going here. So for this one, we have basics. We do the same thing, which is we join it to ratings on tconst. And then we select out these columns. Oops, should fix that. I also selected out is adult here. I don't think I needed to, but I did. I don't follow directions well. This one I'll just show you. If you're like me and you get really annoyed at columns written in camel case, you can relabel them by calling this dot relabel method and then saying snake case so that it looks more Pythonic. What is this, just a single shot? Yeah. You can also write them out individually, but that takes longer. Okay. So this exercise, I think, would actually be interesting to do. This is to take basics and join it to ratings, and then try to compute the top 10 non-adult movies that have the highest average rating that have received at least 100,000 votes, right? So there's a few things you want to do there, right? You want to do a join of something on something. You want to filter on two conditions. One is that the results of that join, right, are probably not adult, right? What is the type of that? That's an integer. And similarly, you want to do a filter on the number of votes maybe that film has received. And then you'll probably want to do an order by on one of the values. Okay, so if we wanted to compute these, we can join to basics on ratings on tconst. I'm selecting out the columns I want and relabeling them just because I want to. And then I've got a few filters. One is that I want the title type to be movie, because there are also shorts and TV shows and other things, short films in here. I'm filtering out the adult films by setting isAdult equal to 0. and I'm specifying that the number of votes is greater than or equal to 100,000. Notice that I'm using the underscore here, both because I've done the join, but I've also relabeled the column names, and so I need to use the underscore to refer to them. Then I'm ordering by the average rating in descending order, because we want the higher ratings to be at the top. And then just selecting out the primary title and the average rating just for sort of ease of viewing. And you can see from there we get Life is Beautiful, Alien, Apocalypse Now, Top Gun Maverick. So these are some popular films. I think if you go to IMDb right now, on whatever day we pulled this data, those are not the top 10 films, because we subsampled all of those titles down to just 5% of the data set. So we're missing a whole bunch of them. So how we go about actually running this computation against the entire data set, I'll show you that very quickly. So I have my answer in this variable called solution4. Don't try to run this next bit unless you have my Snowflake credentials, because it won't work. But just to kind of show you that this is portable. So if I create a Snowflake connection instead of the DuckDB connection, and if that Snowflake connection, well, hopefully works, yes, has the title, the table names, and the correct schema, right? So here's IMDb title basics and IMDb title ratings. If the table names are the same, and those tables have the same columns and data types as what I did locally, then I can show you that if I turn off interactive mode and I call unbind on this expression, which just means remove it, make it less specific to DuckDB in this case, you can see that what that expression actually was two tables. One table called IMDb title basics that has these columns, a table called ratings that has these columns, an inner join, a selection, a rename, another selection. Here are the filters. Title type is adult, num votes, a sort by average rating, and then a selection out, right? All those things are sort of abstract operations. There's nothing about those that are specific to a particular engine. They're just things that a lot of SQL engines can do, which means I can use Snowflake to execute the same expression that I built against DuckDB, except running against the full data set, and I will get the kind of correct top 10 results, because this data are not subsampled. This is the full data set. Right? So you can have a subsample for local development, exploratory data analysis, kind of tune your query on something on your laptop, and then run the entire thing on a much larger engine that isn't your laptop, whether because you don't have data access or because it's going to take way too long. So you can sort of do something on your laptop and then burst to the cloud or do whatever local Postgres thing you've got. These things are portable and move around so long as the table names and the schema match between the two systems. That's the caveat. Okay. How are people feeling? Okay? Little glassy eye? That's okay. It's early. All right. So next up, selectors. Guillaume asked a question in the first notebook, is there a way to not type out all these column names? It's kind of annoying. This is how. So we import selectors as S, just as by convention. If we connect to that Penguins database again and load up, whoa. This is what happens when you don't delete your connection. Sorry, just going to restart that notebook server. Okay, so the Penguins data, hopefully people didn't have to do that too. Oh, I just restarted the notebook server, so just killed the kernel and started again. So we have the Penguins data here, and you can see that there are a few, we've got species and island, those are strings. We have bill length, bill depth, flipper length, body mass, and year. Those are typed as numbers. Sex is typed as a string. So selectors are different ways of selecting groups of columns based on criteria. So in the case of numeric, if I say s.numeric means give me a selector of all numeric columns. And that will give me all the columns that are typed as some kind of number. You can be more specific and say, like, only of the type that are, say, integer 64, and you'll only get the int 64 columns. Or you can do sort of stringy things if they have, with the column names, and say ones that end in, say, underscore millimeter, and you'll just get those columns. That's handy already, but you can actually then use like a selector across all these, and then perform computations on them. So in this case, we would do a mutate, call an across selector, and what we're doing is we're saying across all of the numeric columns, perform this operation. And here the underscore comes in again, which is saying for all the columns we've selected, take the column itself, subtract the mean of that column from it, and then divide those by the standard deviation of that same column, which is the z-score. Well, good. Yep. Right, so then that gives us, and notice actually that does it in place. So now bill length, bill depth, flipper length, these are the z-scores of those previous values that are there. Right? So across all the numeric columns, we calculate the z-score. We've also calculated the z-score of the year, which doesn't make a lot of sense because it's not really a number in the grand scheme of things. So for instance, we can compose those selectors and say we want to go across all of the numeric columns and not specifically the column year. So s.c is just like give me the specific column, or it could be ends with EAR or something, and then compute the z-score of those. And you can see we get the z-score of only the numeric columns that actually have proper sort of numeric data we care about and aren't sort of just a signifier of a time period. What? Oh yeah, that's a good one. So here's, sometimes SQL is very concise, and I'll hand it that. Sometimes SQL looks like this. So don't do this by hand, please. Okay, in the interest of time, I'll show you some of these solutions here. This one was lowercasing all the string values across all the string columns. So we're going to do an across of the columns that are of string type, and then just call lower on them. And so that lowers all of the values of each of those columns. Same if we wanted to do the same thing we did above with the z-score, but we wanted to group that over the penguins on the islands. The selectors work exactly the same way. We just include a group by like we did in the previous notebook. So we first group by species, mutate, call the same selection across the numeric columns that aren't year, and compute the z-score. So a lot of these things are really easy to they should all stack together. And so as you kind of learn more tricks, you can stick them together, and it gives you ways to very quickly perform sort of higher cardinality analysis. Yeah. All right. This last notebook was going to be also exercises, but I think I'll just run through it because we're running pretty low on time. I would recommend looking through this data. It's a lot of fun. This is the PyPI download data. Actually, I should mention the penguin data is from Alison Hill and Alison Horst. Should attribute your data sources. And this is Seth Larson made these available on this GitHub repo here. So this is PyPI download data from whenever we pulled it a few weeks ago. We have 5 or 6 Parquet files. I'm just going to read those in. So you see we've got a table of wheels, scorecard checks, packages, package URLs, maintainers, and deps. So you can see the deps is a package name, the version, if it's available, the name of the dependency that package has. Maintainers are There's a table of like the maintainer's PyPI username and the package they maintain. And maintenance here means you have write privileges to this package on PyPI. And then the packages themselves are what you would expect: package version, which Python version it requires, whether there's a yield, whether it's been yanked, whether it has a vulnerability it's been reported, some useful information. One thing that happens sometimes is if you do know SQL, or if someone you work with knows SQL, they might have given you a query to start with. And if you need to use that, you need to use that, right? Like that's, if you work with a database admin or someone, data engineer, and they give you something, that's your starting point. .SQL is a way that Ibis gives you as an escape hatch that lets you use Ibis, but starting from either SQL or inserting SQL in the middle, but lets you kind of stay in Python land. So it's just the one line of SQL in there. For instance, DuckDB has specifically a Jacquard function for doing Jacquard similarity checks on strings. Ibis doesn't expose this because only I think DuckDB has this, and it would be sort of a strange thing. We might put it in at some point, but this line wouldn't work. There is no Jacquard function to call. So I can instead say packages.sql and then write this SQL statement, which is select name version, Jacquard packages.name, looking for pandas, similarity to pandas, as sim from packages. You can specify the dialect here. If you're familiar with a particular SQL dialect, you can actually write in one dialect and we'll translate it to whatever dialect you say this is. So you can mix and match. If you don't know about SQL dialects, stay that way. It's a dark hole. That did not work. Oh, order by. Yep. So this just called Jacquard similarity on every package in here. And you can see that the package name 0, which I can't believe exists, has a 0 similarity, at least at 6 decimal points to the name pandas. Others have a closer one than you would expect. I wouldn't expect this to be that close, but some letters overlap. We can order that by that column in descending order, and you can see just how many typo squatters there are for pandas. And the answer is a lot. This is actually just the first 10 rows. This list keeps going. So please be very careful when you're typing. Not all of these are malicious, but most of them are. So things to be aware of. Always use Ibis before you install anything else using pip. That's bad advice, but check. And so you can see, you can similarly do, they have a Jaro similarity. Jaro Winkler, okay. You can see this one actually shows you fewer typo squatters and more sort of like the various pandas add-ons, like kpandas and ipandas and fpandas. And then if you want to know how many maintainers on PyPI have usernames that are similar to yours, in case anybody's trying to, do kind of name collision there. Apparently, I'm very close to Photo Froggy. I had no idea. All right. Here's a demo. I realize I think my install instructions are a little wrong. You need a dev version of Altair for this to work because there was a bug. But just to sort of show Ibis does play well with the rest of the PyData ecosystem, if we compute the number of packages that have n maintainers across all packages, we can look for packages that only have certain numbers of maintainers and then plot that using this dev version of Altair as a histogram. And you can see that, well, there are probably too many packages that only have one maintainer. So we should, that's not great. There's also this really weird spike at 12. And that's an odd one. We dug into that a little bit. I'll show you in a second. Or maybe I'll leave it as an exercise. Similarly, plot 9, you can do, if you install plot 9. Yeah. See if you can tell which of these I was writing like in an airport yesterday. Yeah, so that's that same plot using plot 9. And I should point out, these are what I'm passing here to ggplot or plot9 is an Ibis expression. What I'm passing to Altair is an Ibis expression. If you want to use any of the amazing other plotting libraries that are available, you can, of course, always call to pandas on this, and that will make it work with everything. We're in the process using the new Dunder data frame kind of API layer to make this work well with other things. But if you just want to use like the plotting package you have, just send it in as pandas or as PyArrow, and that works fine. Yeah, that maintainer thing, this would have been a long exercise, and we're very close to time. But if you group by package name and you look for maintainers and then filter to packages that have those 12 maintainers, you start noticing a few patterns at about 20 rows, which is there's like these Bob things. There's all these FTW things. You're like, well, that's a lot of FTW. So if you then sort of say like, well, how many packages do start with FTW? The answer is 121 out of 229 packages that have 12 maintainers. Now, that's a lot. And so then if you look distinctly at these names, you just start Googling around these people. And this is the Plone project, I think. And they have 12 maintainers. They have a lot of packages, and all the maintainers have write privileges. So that's what that spike at 12 is. I just thought that was interesting. There's no like a... OK, really quickly as a demo, UDFs, user-defined functions. So sometimes you want to do something that your SQL database doesn't support, and you want to be able to kind of inject a function for it to execute. So for instance, if we have this PyPI data here, these are the top 10 packages by downloads at the time we pulled this data a few weeks ago. You'll recognize one or two of them. A good chunk of them are for AWS. And we can import UDF, and then we can define a scalar UDF in Python. You can also do this for PyArrow UDFs. There are many ways to define these. And say, for each name and version we're going to pass in, hit the PyPI API for that package, and then return whether the listed version that we have is equal to the most recent version of that package. Okay. So I'm just, this is just some requests, munging in here, but basically trying to see, is the list of packages we have up to date or not? So DuckDB is going to take that, and it's going to hit PyPI 10 times. And you can see that most of these packages have been updated since we pulled this data like 2 weeks ago, which makes sense. But so, yeah, if you were wondering, like, can a SQL database hit the PyPI API? Like, the answer is kind of yes. DuckDB can. Similarly, if you wanted to use, like, the PyPI vulnerability listing, you can do that. And, for instance, look up whether there are any vulnerabilities listed for any of the versions of the packages you have. So that's basically checking, is there content in this vulnerabilities field for each of the packages I'm looking up? And then sort of just pull it out. And so I've got, this is a UDF that has a dictionary comprehension inside of it. You can pass arbitrary Python in, including, for instance, if you had a classifier or something like scikit-learn or PyTorch, you can do those and use those to kind of hook your SQL database up to your pre-trained classifier and get results out. In this case, we can determine that actually sort of as always, Certify has vulnerabilities against it. Most of these are totally bogus CVEs that never should have been filed. But if you want to test whether PyPI is working, you can always check to see if Certify has been listed. I won't show a bunch of these because we are at time. I will show you the top 20 packages that only have one maintainer. So this is our bus factor query. So in case you were curious, all of these lovely packages only have one listed maintainer on PyPI. That's not a judgment call. I'm just saying things to be aware of. OK, thank you, everyone, for your time. I really appreciate it. Those Post-it notes we gave you, if you have any feedback, we'd love to have it. Feel free to write a little note on there. You can be mean if you want to, but constructive is better. And Philip and I will be around for the whole conference. We're happy to chat to anybody about anything. And if you have any questions, please come find us. OK, thanks very much. Oh, and sorry, we've got stickers, too. If you want a sticker, please come grab one.